Good morning to you all, dear students. You are welcome back to class. Here are the objectives of our lesson for today. At the end of today's lesson, all of you should be able to state Faraday's second law of electrolysis. All of you should be able to express Faraday's second law of electrolysis mathematically. You should all be able to do some calculations using Faraday's second law equation or formula. You should be able to do some calculations using equation method. You are going to enjoy today's lesson. Let's start the work. I bring to you Michael Faraday. This is Michael Faraday that invented electrolysis that we're talking about. He's an English scientist and he was the first to describe electrolysis in 1833. This man was born in 1791 and he died in 1867 at the age of 76. Electrolysis was not the only achievement of Michael Faraday. In 1831, Michael Faraday invented electric generator, and that was during the Second Industrial Revolution. So, he's among the inventors of the Second Industrial Revolution. Michael Faraday came from a very poor home, very poor family, but he worked very hard to become one of the greatest scientists in the world history. The symbol that we use in electrolysis, which is Farad, was named in honor of Michael Faraday with the symbol capital letter F. Faraday's second law of electrolysis states that when the same quantity of electricity is passed through different electrolytes arranged in series, the amount in moles of each element deposited at the electrodes is inversely proportional to the charge on its ion. So we can express this statement mathematically, and you will recall that there is a word used there, electrodes, meaning that we have more than one electrode. So we have discussed about electrode, we have the anode and we have the cathode. So one element will be discharged at anode, the other one will be discharged at the cathode. So mathematically, how do we express this law? What we are saying is that the amount in mole is inversely proportional to the charge on the ion that is discharged at the anode or at the cathode. So N in this formula means the amount in mole, while C is the charge on the ion of the elements. So by the time we introduce proportionality constants, then we have N to be equals to K over C. What is K? We can make K subject of the formula, and that we then make K to be equal to the product of the amount in mole and the charge on the ion of the element discharged. So K is our proportionality constant. But if the same quantity of electricity is passed through two different electrolytes, then you can say the amount in mole of the first element times the charge on the ion of the first element is equals to the amount in mole of the second element times the charge on the ion of this element of the second element discharged, which means that the product of the amount in mole and charge of the first element is equal to the amount in mole of the second element times the charge on the ion of the second element. So this can be our equation number 3. But don't forget that amount in mole, which is N, is equals to the mass of the element over the relative atomic mass, or if you like, the molar mass. So if N is equal to small letter m over capital letter M, capital letter M in this case is atomic mass or relative atomic mass or molar mass, while small letter m is our molar mass. So amount in mole is equal to this. So meaning that we can substitute mass over molar mass for N in this equation number 3, and we are going to have what? We are going to have mass of the first element divided by the relative atomic mass of the first element times the charge on the ion of the first element equal to mass of the second element divided by the relative atomic mass of the second element times the charge on the ion of the second element, and this can be our equation number 4. So M is mass of the element deposited, capital letter M is molar mass or atomic mass of the element deposited. M1 and small letter M1 and capital letter M1 are what? Mass and molar mass, or if you like, atomic mass of the first element deposited respectively. So small letter M2 and capital letter M2 represent what? Mass of the second element, while capital letter M represents molar mass or atomic mass of the second element deposited respectively. Let's look at some examples on how we can use Faraday's second law of electrolysis to do some calculations. Let's start with this question. Calculate the mass of lead that would be deposited from a solution of Pb2+, that's lead 2 ion, salt, by the same quantity of electricity depositing 1.35 gram of copper from a solution of Cu2+, that is copper 2 ion salt. If the relative atomic mass of copper is 63.5 and that of lead is 207, don't forget that 1 Faraday is equals to 96,500 coulomb per mole. And don't forget what Faraday's second law of electrolysis says, that if the same quantity of electricity is passed through different electrolytes that are connected in series. So we have two different electrolytes. We have an electrolyte that contains lead 2 ion salts, and we have the other electrolyte that contains copper 2 ion salt. So these two electrolytes are connected in series. So we are asked to calculate the mass of lead that will be deposited by the same quantity of electricity that has deposited 1.35 gram of copper. So how do you do that? Let's look at the solution. First of all, copper 2 ion will gain 2 electrons to form a metallic copper. And what does that mean? 1 mole of copper ion will gain 2 moles of electron to produce 1 mole of metallic copper. So 2 moles of electron is equal to 2 Faradays, but 1 mole of copper, of metallic copper, is equal to 63.5 gram. So 2 Faraday is equal to 2 times 96,500 coulomb, and that is equal to what? 193,000 coulomb. For lead 2 ion, we gain 2 electrons to form a metallic lead. What it means is that we have 1 mole of lead 2 ion gaining 2 moles of electron to form a 1 mole of metallic lead. 2 moles of electron is equal to 2 Faradays. 1 mole of metallic lead is equal to 207 gram. So 2 Faraday is equal to 2 times 96,500 coulomb, and that is equal to 193,000 coulomb. So what do we do? From the equation here, 193,000 coulombs of electricity will produce what? We deposit 63.5 gram of copper. So 193,000 coulomb of electricity will deposit what? 63.5 gram of copper. So if the new mass of copper in the question is given to be 1.35, what quantity of electricity will produce that? That is what we are looking for. So by the time the mass of copper is reduced to 1.35, what quantity of electricity will produces it? And that is what we are looking for. But don't forget that the law says that the amount in mole is inversely proportional to the charge on the ion, meaning that when the amount in mole increases, the charge on the ion decreases. When the charge on the ion of the element increases, the amount in mole decreases. So they are inversely proportional to each other. So we can then apply cross multiplication to get the value of X, and that will be what? 1.35 gram times 193,000 coulomb divided by 63.5. You know, this and this, they are with each other. So what will then be the value? Of course, gram will cancel gram, and then what do we have? The product of these two will give us 260,550 coulomb divided by 63.5, and then the quantity of electricity that will discharge 1.3 or deposit 1.35 gram of copper is equal to what? 44,103.15 coulombs, which means that 4,103.15 coulomb of electricity deposited 1.35 gram of copper. What mass of lead will this same quantity of electricity deposit, since the same quantity of electricity pass through these two electrolytes that are connected in series? So if this quantity of electricity had passed through the copper to deposit 1.35 gram, what mass of lead will lead deposits, because it has passed through the two electrolytes simultaneously? So let's look for the mass of lead that it will deposit. So for lead, we have from the equation here that 193,000 coulomb of electricity will deposit 207 gram of lead from the equation here. All of you can see this clearly. So that is what we have here. But now that we have seen that this is the quantity of electricity that had passed through copper electrolyte and has deposited 1.35 gram of copper, what mass of lead will this quantity of electricity deposit? And that is what we are looking for. So if the quantity of electricity is 4,103.15 coulomb, what mass of lead will it deposit? So make X the subject of the formula, and that will be what? 207 gram times 4103.15 coulomb divided by 193,000 coulomb. So coulomb cancel coulomb. Look for the product of these two, and you are going to get what? 849,352.05 gram divided by what? 193,000 coulomb, and it will give you the mass of lead to be what? 4.40 gram. 4.40 gram. So the mass of copper that is deposited when 4,103.15 coulomb of electricity pass through it is 1.35, and the mass of lead that is deposited when 4,103.15 coulomb of electricity pass through it is 4.40 gram. Let's move on. Oh, Oluchi, what happened? Why are you holding your cheek? Oh, excuse me, sir. I don't like the equation method. Let us use the formula method. Oh, by the time we use the formula method, then you will discover that both the equation method and formula method will give you the same answer. Oh, all right, no problem. Let's move on. Let's try the same question with formula method. All right, let's solve the same question using formula method. Remember, the question is calculate the mass of lead that will be deposited from a solution of Pb2 plus salt by the same quantity of electricity depositing 1.35 gram of copper from a solution of copper 2 iron salts. If atomic mass of copper is 63.5 and atomic mass of lead is 207, and 1 Faraday is equals to 96,500 coulomb per mole. So how do you solve this? The first thing you need to do, remember, is to write the equation, which we have done before. So you remember, copper 2 ion, we gain 2 electrons to form metallic copper, and that is 1 mole of copper 2 ion gaining 2 moles of electron to form 1 mole of metallic copper, and 2 moles of electron is equals to 2 Faradays. 1 mole of copper is 63.5. 2 Faradays 2 times 96,500, which is equals 103,000 coulomb. We have done that before. Lead 2 iron will also gain 2 electrons to form 1 mole of metallic lead. That's 1 mole of lead, 2 iron, 2 moles of electron, 1 mole of metallic lead. 2 moles of electron is equals to 2 Faraday, but 1 mole of lead is equals to 207 grams. So 2 Faraday is equals to 2 times 96,500 coulomb, which is equals to 193,000 coulomb. So, but since we are using formula method, we are going to have what? MCU over capital letter MCU times CCU is equals to MPB divided by capital letter MPB times CPB. You remember in the equation we had M1 over capital letter M1 times C1 equals to M2 over capital letter M2 times C2. C1 represents the first element, C2 represents the second element, and we already know the name of those elements. So why don't you replace 1 with CU and PB with 2 with PB? So if you do that, substitute those values, those variables by their values. Mass of copper has been given in the question to be 1.35, and the charge on the ion of copper has been given here to be 2. Atomic mass of copper has been given in the question to be 63.5. So by the time you put them together, you have this. Mass of lead is what we are asked to find in the question. This is it. Mass, we have to calculate mass of lead. But atomic mass of lead has been given to be 207. Charge on ion of lead has been given here. From the equation you can see it is 2. Is a divalent melter. So by the time you put this together, 1.35 times 2 will give you 2.70 divided by 63.5, and the MPB times 2 will give you 2 MPB divided by 207. Make MPB solve the formula. You have what? 2.70 times 207 divided by 63.5 times 2, and that will give you what? 558.9 divided by 127, the mass of lead that would be deposited from a solution of Pb2 plus salts is equal to 4.40 gram. So this answer is not different from what we had when we used formula method. Oluchi, what is the problem again? Oh, thank you very much, Mr. Ademola. Now I understand and can use the two methods very well. Oh, thank God, thank God. That is my duty. I must make sure that you understand the work very well. Let's look at another example. Let's look at this question. A certain quantity of electricity was passed through 2 electrolytic cells connected in series and containing molten magnesium chloride and molten aluminum chloride respectively. If 1.2 gram of magnesium was deposited in the magnesium chloride cell, what mass of aluminum would be deposited in aluminum chloride cell? Take the atomic mass of magnesium to be 24 and that of aluminum to be 27. So what do? The first thing to do is to write the equation of the ion of the element deposited at the 2 electrodes. So don't forget aluminum is trivalent metal. So, and because of that, it will gain 2 moles of electron to form 1 mole of its metal. So 3 moles of electron, 1 mole of aluminum, metallic aluminum is formed. So 3 moles of electron is equal to 3 Faradays per 1 mole of aluminum is equal to 27 grams. 3 Faraday is equal to 3 times 96,500 coulomb, and that will give you 289,500 coulomb. So magnesium is the second element, that is, and so ion of magnesium is Mg2 plus, and it is a divalent melter. So it will gain 2 moles of electron to form 1 mole of metallic magnesium. So we have 1 mole of magnesium ion gaining 2 moles of electron to form 1 mole of metallic magnesium. 2 moles of electron is equal to 2 Faradays. 1 mole of magnesium is equal to 24 grams. 2 Faraday is equal to 2 times 96,500 coulomb, and that is equal to 193,000 coulomb. But that is not the end of the work. You have to go further. So from the equation here, we can see that 24 grams of magnesium was deposited by 193,000 coulomb of electricity. You can see that in the equation here, and that is what is written here. But in the question, we have been given another mass of magnesium that was deposited by a quantity of electricity that is not known to any one of us. We are to determine that. So how do you do it? 1.2 gram of magnesium was deposited by X. X is not known to us. So make X subject of the formula. We are going to have 1.2 gram times 193,000 coulomb divided by 24 gram. So gram will cancel gram, and then we have the product of these two to be this divided by 24, which will give us the final answer to be 9,650 coulombs. So the quantity of electricity that is not known to us before, we've been able to get it here. And so this is the quantity of electricity that passed through the two cells and deposited 1.2 gram of magnesium. So what mass of aluminium will this quantity of electricity deposit? So we don't know, and we have to find it. So let's look at it. For aluminium, we can see that in the equation here, 27 gram of aluminium was deposited by 3 Faradays, which is 289,500 coulomb. So, and that is what I have here. 27 gram of aluminium is equal to 289,500 coulomb. So if this quantity of electricity is the quantity of electricity that passes through the two electrolytic cell and had deposited 1.2 gram of magnesium, what mass of aluminium will it deposit? So we don't know it. We represent that with X. So X gram of aluminium will be deposited by this quantity of electricity. So how do you get X? Make it subject of the formula. Then we have 27 gram times 96,500 coulomb divided by 289,500 coulomb. So coulomb cancel coulomb. Then the product of these two will give you this. So the mass of aluminium that would be deposited by this quantity of electricity is equal to 0.9 gram. So if we use the formula method, we are going to get the same answer as what we have here. SS2C, what happened again? Infonaya, why are you looking like this? Peace, why are you biting your fingers? Michelle, what happened? Can you people tell me what the problem is? Oh, please use the formula method. Let's see if it will be the same. Okay, no problem. We are going to get the same answer. I tell you that we are going to get the same answer as what we got earlier. Let's see if we are going to get the same answer if we use the formula method. Remember, the question is this: a certain quantity of electricity was passed through two electrolytic cells connected in series and containing molten magnesium chloride and molten aluminum chloride respectively. If 1.2 gram of magnesium was deposited in the magnesium chloride cell, what mass of aluminum would be deposited in aluminum chloride cell? Take magnesium, atomic mass of magnesium to be 24 and that of aluminum to be 27. So what do you do? Remember, the first thing is to write the equation of the ion of the elements deposited. Aluminum is deposited and is trivalent metal, so it will gain 3 moles of electron to form 1 mole of metallic aluminum. We have done that before. So 3 moles of electron, 3 moles of electron, 1 mole of aluminum. 3 moles of electron is equal to 3 Faradays. 1 mole of aluminum is 27 gram. 3 Faraday is equal to 289,500. Magnesium is a divalent metal. It gains 2 moles of electron to form 1 mole of magnesium. That's 2 moles of electron is equal to 2 Faradays. 1 mole of aluminum is equal to 24 gram. So 2 Faraday is equal to 193,000 coulomb. So don't forget our formula will be mass of aluminum divided by atomic mass of aluminum times charge on the ion of aluminum equals to mass of magnesium divided by atomic mass of magnesium times charge on the ion of magnesium. So we are to calculate the mass of aluminum. That is what the question is asking us to look for. If the atomic mass of aluminum is 27, which has been given in the question, and the charge on the ion of aluminum is 3, this is the charge, equals to mass of magnesium, which was given here to be 1.2 gram, and atomic mass of magnesium, which have been given to be 24 and doesn't change, times the charge on the ion of magnesium, which is the 2 that you see here. So what will you have? Mass of aluminium times 3 will give you 3 mass of aluminium divided by 27, and 1.2 times 2 will give you 2.4 divided by 24. So make mass of aluminium, solve the formula, and you are going to have what? 27 times 2.4 divided by 3 times 24. Product of this will give you this, product of this will give you this, and mass of aluminium deposited will be what? 0.9 gram. So the answer that we have here is not different from what we had when we use equation method. Let's look at one more example before we call it a day. Let's look at this question. In an electrolytic process involving aqueous solution of copper 2 tetrasulfate 6 CuSO4, if 1.2 gram of copper was deposited, calculate the volume of oxygen liberated at STP. By the way, STP means standard temperature and pressure. Given the molar volume of gases at STP to be equal to 22.4 dm cube, dm cube means decimeter cube, and atomic mass of oxygen to be 16, atomic mass of copper 63.5, 1 Faraday equals 96,500 coulomb per mole. So what do? The first thing that must come to your mind, or that you must recall, is that we talked about electrolysis of copper 2 tetrasulfate 6, and I remember that I told you during the lesson that at anode, hydroxide ion is discharged and oxygen gas is liberated. At cathode, copper 2 ion is discharged and copper is deposited. So the equation will look like this. Copper 2 ion is discharged. It gains 2 moles of electron to form 1 mole of metallic copper, and that happened at the cathode in the electrolysis of copper 2 tetrasulfate 6, which we have discussed in this class. And at anode, hydroxide ion was discharged. It gains 4 moles of electron to liberate oxygen and produce 2 molecules of water. That's at anode. So let's take it from this equation. 2 moles copper 2 ion rather gain 2 moles of electron to deposit 1 mole of metallic copper. That's 2 moles of electron, which is equals to 2 Faraday, and 1 mole of copper is equals to 63.5 gram. 2 moles of 2 Faraday is equals to 2 times 96,500, which is equals to 193,000 coulomb. So don't forget that 2 Faraday is equals to 193,000, and it will deposit what? 1 mole of copper, which is 63.5 gram. As you can see here, 63.5 gram of copper was deposited by 193,000 coulombs of electricity. So if that is the case, from the equation we can see that 63.5 gram of copper was deposited by 193,000 coulombs of electricity. So if the new mass of copper is 1.27 gram, what quantity of electricity will deposit such mass? So what we need to do is to look for the quantity of electricity that will deposit this by making the quantity which is not known to us subject to the formula, and then we are going to have what? X to be equals to 193,000 coulomb times 1.27 gram divided by 63.5 gram. Gram will cancel gram. The product of this and this will give us this value divided by 63.5, and that will give us the quantity of the electricity to be what? 3,860 coulomb. Now, don't forget that 1 dm cube is equal to 1,000 centimeter cube, and we can see in this equation that 4 moles of electrons were lost by 4 moles of hydroxide ion and liberated 1 mole of oxygen gas. So 4 Faraday, which is equivalent to 4 moles of electron, we liberate 1 volume of oxygen gas, which is 22.4 dm cube. And don't forget, if you convert dm cube to centimeter cube, it will be 22.4 times 1000, and that will give you 22,400 centimeter cube. So in other words, what we are saying is that 4 moles of electron, which is equal to 4 Faraday, liberated 1 volume of oxygen gas, which is 22.4 dm cube. So, but if this quantity of electricity passes through this particular electrode, the anode, what volume of oxygen will it liberate is what we are looking for. So we can make that quantity subject to formula. So we have 3860 times 22.4 dm cube, or if you like, 22,400 centimeter cube. So this we cancel this, and the product of the numerator will give you 3864.6400 centimeter cube. By the way, you may decide to use 22.4 dm cube straight away and not 22,400. Okay, but what it means is that if you use 22,400 centimeter cube, you will have to convert your answer back to dm cube at the end, and I'm trying to show you what you will get if you use centimeter cube. So the product is going to be 2224 centimeter cube, but you were not asked to leave your answer in dm cube in the question. Since your initial volume is in dm cube, you may need to convert this one back to dm cube by dividing it by 1000. But if the question says leave your answer in centimeter cube, then you can leave your answer as 224 centimeter cube. In our lesson today, we have learned about Faraday's second law of electrolysis. We've been able to express Faraday's second law of electrolysis mathematically. We've been able to do some calculations using Faraday's second law equation or formula. And at the same time, we've been able to do some calculations using equation method. You can send your comments and your question to me through this email address. My name doesn't change. I remain Ibukunolu Ademola. Bye for now.